A couple of very basic announcements before we get started. I just sent you the other two PowerPoints we're going to be using for this chapter. I'll very briefly introduce 9B today, just a little background information before we get into it in earnest. Then exam-wise, the issue is how rapidly we can get in here without putting too fine, because I know that she's always got an arrangement of people that are here. But I'll be here and I'll have the exams with me, and we'll be able to get started, I'm sure. So effectively, I'm only going to have two different versions of the same exam, just for security of the exam. And so we just be two different colors, like white and whatever other color I didn't look. And beg your pardon. We're just going to make sure that wherever you're sitting, whoever is next to you doesn't have the same color. So I'm going to try to do it by rows when I get in here and start handing out exams that way. We'll see what happens. So that's the other note. Depending on how rapidly we get in here, if you need some, and you probably shouldn't, but if you do need an extra few minutes, I'll ask my class that's coming in. They'll be content to wait for an extra few minutes if necessary. Not a problem. Okay? So try to make sure that you have adequate time, in other words, to do this. So we'll start as soon as you get here, and I'm confident you'll have extra time, but I'll make whatever accommodations are necessary. That ends that. So all good. Let's see. And again, I've gotten quite a few. I've met with a few more students, and I've gotten quite a few emails just for clarifications. Please send them. Mondays are very busy days here, as are Wednesdays for me. So if you have questions that you need me to answer, my guess is you'll probably end up seeing them tomorrow morning if you send me any information. It's just I just know what my time schedule is. And I'm up early in the morning. That's when I start answering stuff like that. Okay. So much for that stuff. We'll get on to where we left off. So we're going to see the last of the three animations. I'm going to look at the one we saw initially, that excitation contraction coupling one. Is going to come to the party again. And here we'll be able to discuss this process a little bit more scientifically, and really the relevance of it is going to be sort of something you're going to see. So this was when I first showed you the relationships, and these are some of the important points and why I stress them. So these are the events that basically how we saw last time how effectively we reached an action potential. The whole idea was the nerve signals, and it starts by what they call end plate potentials. That's just enough. You're going to get a response out of the end plate. The big question is, will there be enough signal to basically go past the area of where that end plate or motor end plate is to where it contacts those, and I know the annoying terminology, those voltage gated sodium and then potassium channels. They're all over in every direction. And they set off this effectively a shock wave that goes in every direction and basically rapidly changes, here's the term, polarity of the membrane, rapidly from positive to negative, and then right back again. That was that previous, trying to get out of my clothes, that previous slide is here showing you that action potential. That's what really we're talking about now. How do we marry that to making the muscle work? And that's excitation, contraction, coupling. And what you're going to see is that effectively electrical events will precede mechanical events. Electrical events precede those chemical changes, like the sodium potassium pumps, and those precede mechanical events. That's really important to understand. So you're going to see this particularly in AP2, and I don't know who's ever going to teach it to you or what sort of detail, but when you get to the electrocardiogram part of the program, you begin to learn about the fact that what an electrocardiogram does with what's called the cardiac cycle. And I've given this context to the other classes because we have a lot of folks who are interested in health sciences and people who are interested in nursing and pre-nursing type majors or undecided, wanting to go into the nursing program. If you're able to get there and you want to work in a hospital and you've always wanted to work in emergency room or intensive care or pediatric intensive, it doesn't matter. It's not something you can just go to. It doesn't work that way. To get to critical care areas, you have to be vetted for knowledge, because not everybody's knowledge is the same. And this is what they were doing at UPMC forever. And I assume they're still doing it or something like that. You have to go through an additional training course to know about cardiac meds, and another training course for making sure, when we say vetted, that they have done their due diligence to mean you know what's happening when you look at an electrocardiogram, or you know what meds are involved, what their side effects are, how they are administered, are there any conflicts. And there's an intense training. This is what my first wife went through. It's a 5-day period, 4 days, 8 to 5. You're in school, hour for lunch, homework each night, several hours. On the Friday, you take a test, which you have to pass. If you don't pass it, you're still a nurse, and you go where you want to go, but you can't do critical care. At least you're not there until you pass that test. And you got to go through the whole training program again. That's why we're doing this stuff. Okay, to begin to understand how, and it's very high intensity. So the best way is to prepare you as soon as, and believe me, the nursing department will do the same kind of a thing that's there. This is what we do. Okay, so I'm sorry to go off on a tangent, but I'm trying to give you the idea of the importance. We transmit this along. The whole idea, we're coupling those. So it's propagated along the sarcolemma. Okay, the sarcolemma, those are the T tubules. I'm going to show you them again. The T tubules are part of the plasma membrane, which we call the sarcolemma. What happens is they form those triads with the sarcoplasmic reticulum terminal cisternae. They're not part of the membrane. They're part of the sarcoplasmic reticulum. These are things that are going to be on the test when you take that next test, not obviously tomorrow's test. And it's going to be controlled by voltage-gated channels. Those impulses traveling down the T tubule, triggering or flipping that switch that allows the calcium that's technically not inside the cell, it's being sequestered, held within those wells. So it's not in contact with the cytoplasm. And so too, this unique apparatus of actins and myosins and things we call the sarcomere. And eventually that calcium is the trigger point that, as you will see, will lead to this contract. That's what we're going to look at today, probably more so than anything else, is understand how these cross bridges form and how it actually moves. So, and this is, again, electrical events precede mechanical events. The action potential is electrical, the mechanical events are contraction. So what you're seeing here, as we couple them, here's the motor end plate, here's that branch, that terminal branch of the motor nerve. You'll see very, relatively shortly exactly why this illustration and why the animations are really taken from electron micrographs, real electron microscope stuff. Here's the signal going along the sarcolemma, the plasma membrane of the sarcomere, in that sort of orangish or whatever yellowish color that's there. And that basically, here it's going around all of the fibrils by way of those T tubules, those sort of infolds on either side. They have these big sort of storage well structures we call cisterns or terminal cisternae, chock full of calcium ions, just waiting to be released. And they are, again, part of the sarcoplasmic reticulum. So as it travels down, it triggers those voltage-gated channels. And here's what it looks like when we start. As the calcium floods in, it bonds to the troponin, those plugs that are holding it, and you can see them covering the active sites. When the calcium bonds to the troponin, anything bonding to a protein or protein complex like this is going to change its shape. So the shape change, in the way I do it with the thread and the push pins and all that stuff, is just an analogy for what happens inside. It's trying to give you sort of a way of me describing it so it would help you understand it, I hope. And here's the calcium. Basically, it makes those molecular changes and the thread gets out of the way. And there are the active sites. We're talking about angstroms. We're talking about millions of a meter, tiny, tiny dimensions. They're so close to each other. When those active sites are exposed, they jam to one another immediately. That bond is going because that head is in a cocked or loaded position. your muscles are ready to go. All they need is the trigger to say, hey, I need to move this. So they're ready to contract. And that's part of what we're going to say, why we have to load them, why they're preloaded, and really it's part of how we get them to relax, as you will see. And so once they load and this attachment occurs, bam, like that. It's going to pull the thin filaments called actin toward the midline. That's what eventually you're going to see when we look at the cross-bridge cycle. So again, just to look at this, showing you the points. If you don't recall them, it's not a bad idea to give you the relationship of the T.
Typically, a single motor neuron arising in the brain or spinal cord conducts action potentials that travel to hundreds of skeletal muscle fibers within a muscle. The sequence of events that converts action potentials in a muscle fiber to a contraction is known as excitation-contraction coupling. If we look at a single muscle fiber, we see that an action potential travels across the entire sarcolemma and is rapidly conducted into the interior of the muscle fiber by structures called transverse tubules. Transverse, or T-tubules,
These are all fibrils in
regularly
there
spaced infoldings
that
of the
surround
sarcolemma
the individual
that branch extensively throughout the muscle fiber. At numerous junctions, the T-tubules make contact with a calcium-storing membranous network known as a sarcoplasmic reticulum, or SR.
Here's the triad.
Where it abuts the T-tubule, the SR forms sac-like bulges called terminal cisternae. One portion of a T-tubule plus two adjacent terminal cisternae is known as a triad. The membranes of the T-tubule and terminal cisternae are linked by a series of proteins that control calcium release. As an action potential travels down the T-tubule, it causes a voltage-sensitive protein to change shape. This shape change opens a calcium release channel in the SR, allowing calcium ions to flood the sarcoplasm. This rapid influx of calcium triggers a contraction of the skeletal muscle fiber. Thus, calcium ions are responsible for the coupling of excitation to the contract.
And so that we saw that. So the calcium is basically the trigger point once it's released from where it's stored. When it's stored, we talk about low intracellular calcium. I know the calcium is sitting there inside the sarcoplasmic reticulum, but technically it's not in the cytoplasm or cytosol. So until that voltage-gated channel is triggered by that action potential going down the T-tubules at the junction points on what they refer to as a triad, effectively, at that point, the tropomyosin is going to stay, that thread, that complex is going to block those active sites. And what releases it is when the calcium comes in, as you will see, attaches to the troponin, and then basically exposes those sites. So they cannot attach when the calcium is in the sarcoplasmic reticulum. The language can be confusing between intra and extracellular. So the voltage-sensitive proteins, quote unquote, gated channels and the transverse tubules, their changing shape then allows that calcium to be released. Then the calcium, once it's released, it flows throughout. Now it's in the cell. So now you're at relatively high levels between low levels. Okay? And the calcium concentration, the calcium binds to the troponin, some way, shape, or form, alters its shape, and because of that shape change, that induces the tropomyosin, which and all the proteins are related, to effectively expose the binding sites on the actin. And then, boom, they bind and they cross-bridge almost immediately, as you will see in the last of these three animations. And what happens when they talk about cycling, once they bind to each other, you're going to see that they're going to rapidly, depending on how much we have to use the muscle. I mean, you may not have to use, if I'm just taking this and pushing it out of the way, very, very brief, it may contract a little bit. But if I'm trying to lift something and it's heavy and there's a lot of resistance, I mean, you're going to have to induce more and more of these sarcomeres to be involved, and for the individual ones to shorten more and more till they reach almost a maximum of their ability to function, and then ask more to come to the party. Because of that, we call it cycling. The sarcomere shortens and eventually will achieve the desired degree of contraction of muscle to accomplish whatever the task at hand is, to move whatever we have to move. And obviously, everything we move or we act on has a different amount. It's going to require a different amount of force to be able to move it effectively. That's there. And so what stops it is when there's no more calcium and effectively the signal coming from the nerve to the muscle, generating action potentials, is continuously releasing the calcium and not allowing it to be put back in to that storage area. Muscles require a ton of ATP. So while that is happening, when I had to make something light, or I found that it was very heavy and I had to pull the whole thing, I'm going to need ATP continuously for two reasons. Once those heads fire and attach and the initial movement occurs, what they call pivoting, I have to push more ATP into it to get it to release. And eventually at the very end, I have to push more ATP into it to pump, and that's the term they use. Once you see pump, active transport, to actively transport that calcium back in to that storage well in the sarcoplasmic reticulum, the terminal cistern. So it's a very energy dependent process. I need energy from the nerve to tell the muscle to fire and get an action potential in the first place. And then either to get the muscle to relax or to continually use it, I need additional ATP. And then I got to pump the calcium back in. So there's a lot to understanding muscles that are there. And down the road, we'll even see how we can use one of these processes continually by adjusting the amount of oxygen and usage and breathing and energy flow in something we call aerobic exercise, like you going out on a treadmill, or my 43-year-old, soon to be 43-year-old son, taking 4.5 hours for some reason, along with 40,000 other people, to run a marathon yesterday at DC. 40,000 people at the Marine Corps Marathon. Running. Take an Uber. I mean, I don't know. They came back to the starting point. So here's what happens. How does this all happen? How did it shorten? They've reduced it to 4 steps. And really, you're going to see the animation goes into much more detail than you will have to know for the exam, not this one, but obviously the next one. And because it talks about how the ATP attaches and how it's hydrolyzed or broken apart and what happens to each component. You just have to know that ATP is required to detach when the actin and myosin bond to each other, and that same ATP is required not only to detach it, but to recock the head. That's what I mean. They're preloaded and ready to go, all of them, as you will see. So we call it cross-bridge formation, and this is part of the cross-bridge cycle. So we call them high-energy myosin heads because they're already activated. They're already cocked and loaded, just the way it would be a trigger, just the way you would pull, like you had an older weapon called a crossbow, and you pull the bow and hold it, and when you basically released it, it would fire what they call a bolt, and it was really one of the early forms of powerful weapons in medieval weaponry, so to speak. So cross-bridge formation, high-energy myosin head attaches to that actin filament at their active sites. Once they attach, they will immediately attach, and immediately then the head fires, pivots, contracts, whatever word you want to use. Pivot's the term they use, pulling the actin filaments toward the midline. To detach, we had ATP, okay, and it causes to detach. And they talk about the hydrolysis. Basically, as the ATP is broken apart, effectively that's what happens. It recocks the head. So we're ready to go again. This energy will be used for the power stroke in the next cross-bridging cycle. And it can be continuous, again, depending on how much you have to use it. So this is what it looks like. Here's where the cocked head attaches to, and the active sites come together. Here you can see the pivoting or the power stroke. pulling it, as you can see, toward the midline this way, toward the middle of that sarcomere. Here you can see ATP being added to attach it. And what they're showing you is the ATP breaking apart here. That's not a big deal for us. Again, as you go to more advanced levels, we talk about that. I'll do it in the spring with my advanced physiology class. And here we have separation. And the separation not only is accomplished by the ATP, but by recocking the head. So it's ready to go. Here's what it looks like. And I'll go over this and review it.
The contraction of a skeletal muscle generates the force necessary to move the skeleton. A contraction is triggered by a series of molecular events known as the cross-bridge cycle. In a skeletal muscle fiber, the functional unit of contraction is called the sarcomere. A sarcomere shortens when myosin heads and thick myofilaments form cross bridges with actin molecules and thin myofilaments. The formation of a cross bridge is initiated when calcium ions, released from the sarcoplasmic reticulum, bind to troponin. This binding causes troponin to change shape. Tropomyosin moves away from the myosin-binding sites on actin, allowing the myosin head to bind actin and form a cross bridge. Also note that the myosin head must be activated before a cross bridge cycle can begin. This occurs when ATP binds to the myosin head and is hydrolyzed to ADP and inorganic phosphate. The energy liberated from the hydrolysis of ATP activates the myosin head, forcing it into the cocked position. A cross-bridge cycle may be divided into 4 steps. Step 1. Cross-bridge formation. The activated myosin head binds to actin, forming a cross bridge. Inorganic phosphate is released, and the bond between myosin and actin becomes stronger. Step 2. The power stroke. ADP is released and the activated myosin head pivots, sliding the thin myofilament toward the center of the sarcomere. Step 3. Cross-bridge detachment. When another ATP binds to the myosin head, the link between the myosin head and actin weakens, and the myosin head detaches. Step 4. Reactivation of the myosin head. ATP is hydrolyzed to ADP and inorganic phosphate. The energy released during hydrolysis reactivates the myosin head, returning it to the cocked position. As long as the binding sites on actin remain exposed, the cross-bridge cycle will repeat.
You see the end point.
And as the cycle repeats, the thin myofilaments are pulled toward each other and the sarcomere shortens. This shortening causes the whole muscle to contract. Cross-bridge cycling ends when calcium ions are actively transported back into the sarcoplasmic reticulum. Troponin returns to its original shape, allowing tropomyosin to glide over and cover the myosin binding site on actin.
And so effectively, it's a complicated process, but you don't have to get into all the gory details that are there. They're showing you the cycle. So when we want to move something, we basically function on what we call one motor unit. If that's not enough, we bring other motor units into the play. And typically, it's going to basically that will determine how many of these sarcomeres are going to have to shorten until what you saw was the end point in order to accomplish whatever we're supposed to do with this muscle. And then as you see, after we finish with this idea of understanding how they work, it's kind of like, okay, so what muscles do what, and how do they differ from one another in their ability to do things rapidly or slowly? That's what we get to going forward, to understand the muscle and to understand how it works when it's damaged and when it's working So there, that's sort of the end point, getting it there, the individual sarcomere. The more that are doing it, the more contraction you're going to get. So here are the calcium ions flooding. I would not get excited about the fact that we're going to have to lose this or gain this, but the calciums effectively have caused the troponin to alter its shape, so the tropomyosin then exposes those binding sites as they've described them here on the illustration. The myosin head attaches, the myosin head fires. I'm not worried about, the ADP, the phosphate making it stronger, or the ADP moving so it actually pivots. That's too much information that you don't need to be responsible for. The ATP loads it, and down the road, the ATP has to attach it and reload it. It's loaded from the ATP from the previous cycle. That's how it works. So it's always ready to go. And so the cross bridge forms here. Again, the fact that it tightens because it's releasing inorganic phosphate, no biggie. The second step was the pivoting, the fact that it loses or releases that ADP, adenosine diphosphate, makes the power stroke. Again, not worried about it. They're going to happen rapid. It's going to attach, it's going to firm up, and it's going to fire. And it's all about doing this process continuously that effectively makes what we call the muscle contract or shorten. And so the release is all about ATP. That'll make it separate. And yeah, sure, it hydrolyzes or breaks into its components to recock. All you have to know, it recocks. And then what you have here, and that's why I like it so much, as we're beginning to shorten it more and more. If effectively, you can almost see from this illustration the way that they're offset and the way that things move, so that when one attaches, another one can detach. Again, the analogy like climbing a rope ladder, you can't let both hands go or you're going to fall. So here you always have something attached, and sort of they're offset, the heads are offset. And so it's continuous motion that allows this to contract fully and completely, and then what allows it to relax. Not just the ATPs coming to release it, but particularly the calcium being pumped back in. It's all about the calcium getting out of the way. So you can see the energy dependency of this rather unique process. So that's really the end, almost the end. And the interesting thing is it gives us a clue about a lot of the ways muscle works. So if muscle's preloaded, it explains a really important phenomena. And this is where the forensic or post-mortem aspects are so very, very interesting, and where the tie-in. Just like when we talked about bones, not that I'm going to ask you a question on this coming exam on Wednesday, is this the bone of what would determine it's the bone of a 5-year-old? I'm not going to do that. I mean, that would be a class that we were doing, a forensics class, which I don't know if we have here, but I certainly don't teach it. And it's this phenomenon called rigor mortis, rigidity upon death. And if you go back sort of into the early days of TV, with TV shows in the 50s and 60s, they would refer to a dead body as a stiff because it stiffens after death, whether you've heard that expression or not. The people in my middle class had no idea what I was talking about. So maybe some of you do. Okay. So this is how when a crime scene is observed and they bring in the coroner or they bring in criminal specialists, they immediately, what they look for as they find a corpse is to see if there is rigidity. That is called rigor mortis. It starts under normal circumstances, and it's based on the temperature. If it's really cold, much slower. If it's really hot, much faster. So under normal temperature, even like today, maybe a tad slower because it's cooler. 3 to 4 hours after death, it begins to stiffen. Why? The heads are preloaded. The calcium, we have no way of, the dead person's not giving a signal to release the calcium, but as the body begins to decompose, those storage wells lose their integrity and the calcium floods the interior. So it begins to stiffen. The more calcium, the more, and eventually they become rigid because there's no ATP available. Someone's dead, no longer makes any ATP. That's something that only occurs when because it requires oxygen, when someone is breathing. And at that point, it's going to stay rigid until such time, as you can see, it peaks about 12 hours, And again, depending on those temperature parameters, is it another 12 hours? Is it 15 hours? Is it 20? Whatever. What will happen is the muscles effectively will start to decompose. Their proteins will denature with time and depending on the temperature, either faster or slower. And at that point, the rigidity will go away. So this is the idea. Intracellular calcium levels increase because the ATP is no longer being synthesized, so the calcium cannot be pumped back in. Cross bridges form, ATP needed for detachment. The head stays bound until such time as the proteins break down. So it's really one of the neat things. So they're able to, I mean, if you did not know it, they'll take the internal temperature of the body, they'll look at they'll measure the external temperature, they'll look at it over the X number of days time span and be able to determine when this individual died for whatever the reason. Typically, this is looking at things might be suspicious. Interestingly, if you did not know, stomach contents, as an aside, if you know when somebody ate, you can get a pretty good idea depending on what they ingested, because some things take longer to digest than others. It's a really useful way. And the other thing, that there's another mortis called liver mortis. We call them lividity patterns. And what happens when a person dies, all the blood starts to escape from their blood vessels, and effectively by gravity it stains the skin. So if somebody died in their sleep and they were sleeping on their back and their buttocks, X amount of time after their death would reflect discoloration, get darker, duskier, kind of reddish brownish. That way we know if a body's been moved. If you see that if that forms on somebody's back and you find them face down, guess what? Somebody moved the body. It didn't move itself. Or the other way around. Somebody's lying on their back and they're all discolored here. Something wrong. I mean, sometimes it's easily explainable. Somebody moved the body because they wanted to turn them over to do CPR. Okay, you can buy that. So you got to understand, this is why some of this stuff is so interesting, and it depends on what you're doing in your lives. This may become relevant. I can't tell you, but I think it's obligatory for me to explain it to you. Thus end this particular PowerPoint. Most of the material we have to cover today, it just leaves me some time to do the introductory nugget for the next section. And this is more about some of the way we really analyze muscle movement. So in this, we begin to look more closely at the activity of these muscles to understand how they contract, the nature of it. And these are some really, and the terminology is some degree of significance, as you will see. A lot of what this works on is to understand that the marriage of electrical activity to contraction. So it's sort of a takeoff on excitation contraction coupling. What you will see is there's always a period, and it's tiny in muscles. It even exists in nerves. It's very, very tiny between the signal going from nerve to nerve or nerve to muscle. Even quicker than nerve to muscle is nerve to nerve. But it's the same thing. We release chemicals that basically allow one nerve to talk to each other. Or we release chemicals at the neuromuscular junction to tell the muscle to fire. That's in science we would call the rate determining step. So there's a finite amount of time that we can see by testing the muscle. Okay. And this is something some of you, particularly if you're going to health sciences and physical therapy, it's going to be extraordinarily significant. That's why it's an important part of the program that we here do in any anatomy and physiology. Because it involves some science called electromyography, or capital E, capital M, capital G. And that's a common acronym that you run into. A lot of this is the foundation of exercise science and rehabilitation. If you're in sports, if you had an injury, if you've done rehab, you'll be familiar with, they use something called electrical stim. And they'll put, and this is non-invasive treatment, where they'll put basically pads, like the same way you would put pads lined for electrocardiogram, and basically stimulate your muscle by way of those things. Scientifically, sometimes to find out what's wrong with it, and sometimes to find out how to rehabilitate it or re-educate it. And this is it's a really very interesting area. It's been around it's nothing new under the sun. Low volt therapy has been around for 100 years or more to try to make muscles work a bit better. So when we look, and again, we were able to look at it by looking at a single fiber to understand the muscle. And so the contraction produces tension. Tension means we're beginning to generate a force. The muscle won't move until it could overcome what it's moving against. I mean, here, there's really nothing to oppose it. So almost as soon as the tension develops, I can move this. But it's going to take longer if I'm lifting something, and longer still if I'm lifting something heavy. That's the idea. Okay, so that tension is produced first. So the terms, and these are important going forward, first way that every muscle that we use starts isometrically. Iso means same, metric means length. So the muscle doesn't shorten until the tension, the force we develop in it, overcomes whatever we're trying to move against. Even if we're moving it against nothing, even if we're just gesturing. Because there's still a certain amount that we have to overcome, whether it's whatever the pressure of the air, etc. There's always something to overcome. And so once we overcome it, then the muscle moves, shortens fairly easily. We don't change the tension unless there's an intent to do so. We call that isotonic, so the tension remains the same. So in the old days, before we had elaborate gyms and we had workout machines as well as free weights and things like that, what was very, and I don't know if it's still popular today or if it's used in rehab because it's been 25 years since I had patients, ordering patients into physical therapy and working with physical therapists to do that. Basically, your isometrics were something that people were taught where they could exercise at home without having to have a whole weight set and go to the gym, which would have free weights. Okay, and they wouldn't have all this elaborate apparatus at home. This is called an isometric exercise. So you could exercise your muscles without having to leave your room. If you had and there were lots and lots of books, you can still find them easily. Isotonic is typically, think about you're working with going to the gym, working with free weights, or working with the machines and moving them around, etc. That's more isotonic. Things have changed, even in the way we prepare for things. For years, when you warmed up, you were doing things that were very bouncy and jumpy. It was called ballistic stretching. So, jumping jacks and squat thrusts and things like that. Then all of a sudden it went to static stretching. Now, and this is what happens a lot in science, we go back and we revisit something because maybe there was scientific basis, and they came out with things like Pilates and things like that. So there's a tremendous amount that's involved with it. And by and large, most of the time, it's a marriage of all of these things that really, really contribute to fitness. So for any of you who are going to physical therapy, athletic training, etc., there's so much to understand. So much to understand about that. And it's changed dramatically since I started learning about it. And that's more than 50 years ago. Everything has changed. What hasn't really changed, and that's what we're kind of getting into it, and I'm just going to introduce it a little bit to you, is understanding this whole electrical activity concept. So the force and duration of the contraction vary in response to the stimuli of different frequencies and intensities. Short course. What you're going to learn, and it applies to a certain extent in muscle and to an extraordinarily and effectively all of it when it comes to nerves, is frequency equals amplitude. In muscle, you're going to see once we reach a certain amount of frequency, the amount of the response isn't going to change. But what you hear when I do this, when I yell or something like that, or I speak very softly, that's amplitude, very soft or very loud. Won't do that again. I don't want to disturb Dr. Maurer like that. And that basically is the muscle firing a lot rapidly. That's intensity. Or very, very slowly. So if it's rapid, that's loudness. That's the intensity. That's the power of the muscle. If it's very slow and a little bit at a time, that muscle may not move at all. Okay. So when we talk about nerves particularly and neuromuscular interfaces, frequency is really a major part of amplitude. The nervous system, it's everything. Loud sounds, frequency. Okay. Hurts you a lot, frequency. Because nerves reset very, very rapidly. Muscles rapidly too. So each muscle is served by at least one motor nerve. Axons of hundreds of motor nerves are part of it. Okay, so they can go up to hundreds of motor neurons from one nerve. And they branch and branch extensively, which we talked about before. It's called a motor unit, or what we were looking at. And that's what I mean. We see the illustration. This is what it was taken from. Remember, I was telling you before when we looked at the motor end plate and the nerve, and we looked at that last week, that you began to see those almost like little feet that were sitting on the individual muscle fibers. And so it was taken from an actual electron micrograph. And as you can see, there's more than one motor unit. Here's one particular area of a nerve coming from the spinal cord. You can see this is a ventral horn. You can probably remember that from anatomy. That's where motor comes out, even though the sensory and motor groups come together as one unit there. And there they're spread out over different areas. And so as we need to use more of that muscle, we bring more motor units into play. So the motor unit consists of a motor neuron and all the fibers. The smaller the fiber number, the greater degree of control. So you have just those individual nerves, those individual axons go to very, very few motor units for dexterity, for speaking, for subtle changes in our face. Those are we exert a lot of fine control. When you're walking, you don't. Those are big muscles. They don't need that. They're just designed to move. There's some nuances between them. But if you're standing in line waiting to get into the game or at a cafeteria line, wherever you are, those are mostly postural muscles. They don't have to move a lot whatsoever. So you don't need a lot of fine control. They just have to move when they're needed. And you're going to see that's not the only differences. The composition of the fibers, how rapidly or how slowly they work, all of those play a role. So muscle fibers are spread out the muscle, so stimulation of a single motor unit, only a weak contraction. So when we look at this, we're going to come and start looking at this. This is the basis of the electromyogram. It starts for something that we have occasion that we really only see in the lab, and perhaps only other time we see that if the nerve and the muscle complex has been damaged. That's where we're going to start on Friday. I'll leave you with that. We'll see everybody, as I said, Wednesday as soon as we can get in there and you have a seat. And most of you guys come in somewhat snaggered. You're going to start working on that test.